There's not many recordings for this class because we don't really do that many lectures. So anything we need to go back over? Everybody okay so far? So we got through resistance. So the next thing we're going to look at is the continuity. What we'll look at now is what we're going to do is a diode testing. On our little circuit board, I think we've only got one diode in there, and it's actually a light digital. Yeah, everything else is integrated. So what I've done is I brought a few diodes in here to let you see that this test works on anything. And what we're going to do is we're going to connect our meter leads up. We okay? So you're going to put your black on your common and your red and your, we're going to rotate our dial up to where it says the diode check, which is, it's a p-n junction check, guys. So like I was telling y'all, you can check a lot of things with this besides just diodes. Now what does a diode do? I can't hear you, Maurice. Yeah, it's a check valve. If you're familiar with check valves in any fluid system, it just lets current flow in one direction. So this is the main element. We use it has a lot of uses. We use it for protection and stuff like that. But one of its main uses is to turn AC into DC. So in your car, you got a set of rectifiers in your car because you have an AC alternator out there, but your car operates off of DC, right? So the symbol for a diode is this guy right here. That's the symbol. And to make this thing conduct is you got to make this symbol right here that we refer to as the cathode. This is referred to as the anode. And this came up through vacuum tubes. The first diodes were actually put out by vacuum tubes. And to make this thing conduct, what we have to do is we have to make the cathode negative in respect to the anode by a certain amount of voltage. Then once you exceed that voltage, we call it a barrier voltage. Once you exceed that voltage, then the diode conducts. Anything above the barrier voltage is, and one thing you learn right off the bat is that diodes will never drop 0 volts. They always drop a voltage when they're biased. So in AC, we could pop this across an AC circuit, and we could figure out how to just cut off one of the alternations. This is called half wave. Or we can figure out how to arrange the diodes actually to get what we call full wave rectification. And like I said, we use them. Now, when we look at the LED, we're going to look at the LED, and this is why I brought some regular diodes over here to get you a feel. The voltage drop across the LED is about 2 volts. Remove the battery still out. Okay. And then what we're going to do is we're going to take an LED. You can look really close on the LED. You'll probably notice the symbol for an LED, by the way, is the same basic symbol, but we draw arrows out of it like that. That's the true symbol for a light emitting diode. And normally what they'll do is one of the leads will be shorter, but if you look, I think we can see it on this one. If you look, you'll see that one side is flat. That's hard to see on this one. Yeah, I see it. So one side is that flat, and that flat side is what we want to put the negative meter lead to. So we'll take our meter, we're going to hook it up, we're going to take it, and we're going to place it across the diode like it's shown. So we're going to put the black lead closest to the lead, but if you look at the diode, it's got a flat side on that side. We're gonna put the black lead on the flat side, the side toward the battery terminals, and we'll touch our red lead over to the other terminal. Now, some meters will not check an LED because the VF on an LED is about 2 volts, and some meters on the on scale it won't put out that many voltage. This guy right here will, and you can probably actually see the LED probably will light up, I think, when we do it with this meter. Let me see if my meter will do it. So what do we measure? Huh? Hopefully not 0.7 on the LED. It should be 0.7 on a regular diode. Yeah, 1.5. Rule of thumb is around 2 volts for an LED. So 1. That's perfect, right? So this meter, my Sperry, it don't put out enough current to turn the LED on. So this will only work with some meters. So you can't check LEDs with all meters. Now, when I come up here, let me pass out these little diodes right here. These are small signal diodes. And what you'll notice, there's a black line on one side. You'll see the black line on the side. That's the cathode. So to check this thing, what you would do is you'd put your black lead toward that black line, and you'd put your minus lead, your black lead toward the line, and you'd put your plus on the other side, and then it's going to raise around 6 to 7 tenths of a volt, which is what's standard for most diodes. About 7 tenths, about 6, 7 tenths. And if you flip it around the other way, you should read infinity. So when you check a diode, you should always reverse bias it. You should put it up backwards too, because sometimes these guys will be leaky. And if you measure anything on the back direction, it means you still got a problem. And now what I've got here, guys, these are some sure enough diodes. And what they do on these, since these are big enough, they actually put the symbol of the diode and this, you can't tell if this is negative or this is positive or the cathode or anode, because these are stud mounted diodes and they can make them any way they want to. I don't have enough to give everybody one of these, or we can pass it around. And you'll see, you check these. These guys are going to measure about 5 tenths of a volt because they're heavily doped. But you can check these guys with it. These, you got to spin it around, and the cathode is in the anode. So what we're trying to show you, it really don't make any difference how big the diode is. You can check it with your meter on the diode scale. Are we okay? A lot of people think these guys right here, you can't check these, but you sure can. But you always should do what? If it checks good one way, always put it the other direction, just to make sure the dang thing's not leaking. So we can check transistors, we can check some SCRs. These are silicon control rectifiers, which is what this guy is right here. I've seen diodes this big. And they go in a water-cooled jacket, and you have to compress them for them to work. If this was a regular diode, you can check it without water. You can check it with your meter. So LEDs are going to measure around 2 volts. These guys should measure around 6 to 7 tenths of a volt. If they're silicone, and you're not going to run into many germanium diodes. Are we okay? Pretty cool, huh? That's how fast you can check them, just like that. No matter how big they are. So the only diode that we have on this guy is that light emitting diode. So it's kind of giving us misleading because it's measuring 2 volts. Are we okay? And you always switch them around, just like this guy's showing on there. Are we okay? Good diodes allows flow. It allows current to flow in one direction, but it still drops a voltage. And this is why these big diodes have to be heat sinked. So even though they drop 7/10 of a volt, you put 500 amps through that thing at 7/10 of a volt, that's still, a lot of wattage. So these guys will get hot, even though they're dropping very little voltage. And they're not like a switch, they're solid state. So these guys will always drop a little bit of voltage even when they're forward biased. Overload should show when we go into bad, right? So we should always swap it around. Are we okay there? Everybody okay? Overload or open, or if you get a reading in both directions, especially the same reading. And of course, it should never measure zero. Normally, if it measures zero in one direction, it's going to measure zero in the other. It just means the solid state device shorts. So solid state devices, they can become leaky, or they can open, or they can short. So we got solid state devices can go bad 3 different ways. Okay, that's what diode says. Digital capacitors testing. Sometimes this works, sometimes it don't. A capacitor is basically, it's really cool. It kind of acts like a very small rechargeable battery. But how fast it charges depends on the capacitance, the capacity of it. So the bigger they are, and they're rated in something called farads, basically it's an indication of the ability to store a charge. Or if you think about it like a bucket, it's the size of the bucket. So the bigger the bucket, the more farads it would have, and the slower it would charge into a digital meter. So some of your big capacitors, we can check these with an ohm meter. We can actually put the ohm meter across it, and we can literally see the thing charge. But real small capacitors, they have little capacity. They would charge just like that, and we can't check them with a normal ohm meter unless you put a resistor. But these guys right here in DC, we use them as filtering. Their opposition changes with frequency, so we filter out noises that we don't need. We use them, even on diodes, if I was to come over here and put this, which is what I'd get off AC, we put a big old capacitor on there, then we'd start moving toward DC because the capacitor would filter out all that garbage. So just about every power supply you're going to see diodes, but then after that you're going to see these big old capacitors in there filtered out. Can store energy when disconnected from a charging circuit. Short-term energy storage, they'll actually discharge through themselves. Commonly used in electronic devices, main power supplies while batteries are being charged or changed. So sometimes we actually allow us to change, the capacitors will hold a charge for a small amount of time, and sometimes it'll hold a charge long enough for you to change your batteries out. So we're going to test capacitor testing. This guy has a capacitor checker, so we're not going to use the ohm meter. We're going to actually use the capacitive checker. Connect the black lead to the black and the red lead over to your volts, ohms, and hertz, right? And then move it to cap. Everybody okay? And then what we're going to do is we're going to remove the battery. Battery's out. And what we're going to do is we're going to connect it to terminal 5. So there's a capacitor in here somewhere. And we're going to connect the black lead to the common. I didn't bring any capacitors over here, guys. And then we're going to watch our display. And it says, according to this, we're going to measure around 250 nanofarads. This is a little old tiny capacitor. Are we okay? Any questions? This completes the capacitor test. So this meter has a capacitance checker on it. This one does too. Frequency. So when we deal with alternating current, this is the way it kind of looks when it's generated. And it just keeps repeating and repeating and repeating and repeating and repeating and repeating as long as you have power on it. Well, we call one complete cycle. We call this one complete waveform. We call this a cycle. And then the cycles are occurring at a certain rate, and we call this the frequency. So frequency is the rate of the cycles. And it's actually in cycles per second, but people that's fundamental in the laws of physics had, especially in electrical physics, had the honor of their name be given to certain quantities. So most of the time you're going to hear hertz, and we abbreviate that H lowercase z. So hertz stands for cycles per second. So out-of-hour power, anybody know the frequency for out-of-hour power? Some of y'all should. That's 60 hertz. Over here, if you go over in Europe, it's 50. So what we need to do in variable frequency drives that we find on a lot of our motors now, these guys, that's one of the things they're doing is varying the frequency. And the frequency and the voltage is what sets the speed. How many times per second? How many times per second a signal happens? 8 cycles per second. Example. So this would be. So what they're doing over here is they've got 8 cycles. Now this is not an AC waveform. This is a digital waveform. And so that's exactly what it means. So they're starting their cycles right here. And if this starts the cycle, then it would go from here to here to here to here, right? And exactly what it means. 1, 2, 3, 4, 5, 6, 7, 8. That would be 8 cycles in 1 second. And that's for repetitions, right? Number of repetitions. Duty cycle. One of the things we do now is we come over here and we look at this waveform. So notice on this one, the maximum voltage and the minimum voltage are the same. And these are DC. And what would you think the DC average? If this right here was 10 volts. So let's say up here at the peaks, this was 10 volts and down here was 0 volts. What would y'all think the average DC voltage would be? Exactly 5, because the pulses are exactly the same. And that's exactly right. Well, what would happen if I came over here and made the positive pulse narrower? Well, what would happen is it would see it as a voltage less than 5. Now, what we do is we have this guy right here. We refer to this as the period. And the period is the time for 1 cycle. So if it was 60 hertz, the period would be like 16.777 milliseconds. Then it's constantly changing. Well, what we can do on DC is we can come over here and divide this right here. So let's say this right here is 10 seconds and this is 1 second. Then that means 1 over 10, which would give me what? 1/10? Will give me 100 milliseconds, right? That's not what I want to do. I don't want milliseconds. I want a percentage. So that means that guy would be high 1% of the time, right? That makes sense. Did I lose anybody? Well, the way we configure the calculated way we can fix, so that means my motor would see that as 1 volt, and it would run at the speed of 1 volt. So the duty cycle is the percent of the period that your waveform is sitting at its maximum voltage. And once you do that, if you get the percentage, you multiply it by the maximum voltage, and that'll give you what we call the average DC voltage. This is the main way we use to drive DC motors now. Is using, instead of using a voltage, we use these pulses, and it's a lot more efficient. So the percent of the time the signal is what? On. So if I was to come over here and go 2, right? You understand? So if it's 2 to 10, that would be 2 to 10, and that would be, well, so 2 to 10 each. 2 to 10, so that would be 1/5 or 25, it'd be 25%, right? Does that make sense? So what we like to do is we like to have the ability to measure duty cycle. I think this meter does both of them, right? It measures frequency and it also measures duty cycle. So we're going to look at this. We're going to go to frequency. We're going so what are we going to do? Frequency in hertz. Okay, so notice up here, we get the ability to change it between what? So right here, we get the ability to change it between hertz and frequency and duty cycle. So what we're going to do is we're going to put our, what this button functions can be AC volts and hertz settings. So the connector's up like this. We move it over to what? Hertz, common. Move the rotor dial to hertz. And then what we're going to do is we're going to look at these. So this is AC. I don't know which ones we're going to look at. So can you see the little, that's the symbol for that. And then we have this one. And then we have this one. It looks like this one will get the ability to change the duty cycle. So we're going to start off checking it to the pulse waveform. And then of course we'll put our black lead to the common. Are we okay? And then we'll turn the trainer on. Y'all disconnected y'all's batteries back in there, right? And then we're going to start rotating dial B, and hopefully your frequency should change. So, y'all's jumping around like that? Y'all's okay. Should have B turned, rotate dial B and watch the display. Oh, looks like they're turning it real fast. So what's the highest hertz we can put out of that thing? Or the highest frequency? Kilohertz, and what's the lowest? 5 hertz. Or around that, right? Everybody's what needs that. Are we okay? Everybody okay? Any questions? Now we're going to measure the duty cycle. So we got our meter hooked up the same way, right? We got it raised to hertz. Now we're going to press the duty cycle button. And then we're going to move it over to terminal 2. So terminal 2, you see the little arrow. These are the guys that's going to be able to change the duty cycle. So the higher the duty cycle, the more average DC these devices are going to see. Black, so we're between 2 and 6. And then we're going to be playing around with C and D. Turn simulator on. Rotate dial A. And notice the duty cycle is displayed in the percentage. Look at that. Watch the change in duty cycle when you rotate A. They say B should be set in the center and C should be set in the center. So what's the lowest duty cycle we can generate? Percentage wise? Okay. 0.8. And what's the highest duty cycle we can generate? Huh? 0 is the lowest. And what's the highest? 72%. Are we okay? So we can take this out and run it through a transistor, which would give us some gain, and we could run a DC motor with this pretty easy. So what test should be done on an unpowered circuit and isolated components? So what would we measure with our meter when the circuit is unpowered? What do you think we'd be looking for? Yeah, resistance, right? And why? Because you can mess up your meter if you put it in a powered circuit. What is the threshold resistance value in order for the continuity to beep for this meter? I remember? That's 30 ohms. It's the good and bad diode test values. So your good value is not going to be continuity. It's going to be whatever's required to cause the thing to work, right? Normal diodes is going to be around 6 to 7/10 of a volt. LEDs is going to be around 2 volts. And remember, some of these meters will not put out 2 volts on the ohm scale. If these guys don't put out enough voltage, these will not check LEDs. So this meter right here will not check an LED. So just because you get your meter out and you check an LED and it comes up and gives you overload both directions does not mean the LED is bad, unfortunately. So what rotary dial setting is used for frequency? The one that's labeled what? Frequency, yeah. What rotary dial is used to test capacitance? And that would be the capacitance check on this guy. If it don't have that, you can check big capacitors with an ohm meter. Are we okay? Are we okay? Everybody okay? Additional functions: record, release, hold. And that's on this meter. And of course, the test is on this meter. So you might have other functions on your meter that this meter don't have. Or this meter might have some functions that that your meter has, right? So record and capture two extremes. So this is what the record button does. So what it does, it's going to detect the maximum value that your meter ever sees, and it's going to detect the minimum value that your meter ever sees. Max, high, or maximum reading for the scale that you got, minimum, low, or minimum reading. Used for rapidly changing signals. Voltage drop, intermittent issues, and etc. So this guy works on all, we can use it on volts AC, volts DC, millivolts AC, DC. We can use it on ohms or resistance. We can use it on all our amp scales. This record button will work on everything, right? Except hertz and capacitance. So we record AC as an example, but remember it can be used on any electrical measurements in circles. So we're going to hook up our meters. Meters should already be connected like this, right? We okay? And then we're going to move the rotary dial to AC. And then what we're going to do is we're going to put our red lead on terminal number 5. We're going to put our black lead on terminal number 6. And then we're going to turn B. We're going to turn B maximum and minimum. So we'll start off straight up. We'll start B up straight up. Then you're going to hit the record button on your meter. And then you're going to rotate B all the way right, all the way left, and then back to center. And it should hold both of them, right? Are we okay? Any questions so far? Yes, no? Okay. So how do we get max? The max value is displayed by default. So that should be your maximum value. According to this, we got about 1.4 volts. I don't know what yours got. And then we press the record button once. Don't hold it down, just press it once. And then it should switch and show you the minimum value. Are we okay? Does this make sense? We okay? Hearing a lot of beeping out there. Are we okay? Okay, so that's a neat feature. So you don't know what happens between those values, but now you can record the maximum value and the minimum value. Continue pressing the record button. You can switch back and forth, back and forth. So how do we get this off? Are we okay? So relative is a neat feature. What relative does is it measures relative to some voltage that's already there. Are you okay? So 0, the display, if desired, we'll show you. Can be used to see the change or the delta change in electrical signal as compared to a relative point that you establish. So this works with all the measurements, even capacitance on this one. Next we'll form the relative DC test as an example. Remember, it can be used with any of the electrical measurements circled above. So we're going to hook up our meter. So hopefully we've got this already hooked up, right? And then what we're going to do is we're going to look at DC volts. And then we're going to hook up our red lead up to number 4, which is the DC output. We okay? Now, of course, we're going to connect our black lead over to common. And then we're going to set dial 4 into the center position. So maximum. Are we okay? We okay? Then we'll turn on the trainer. And then what you should measure a voltage there. Everybody okay? So and then when you press the relative button, what happened? It should go to 0, right? Because that's what we're doing. We're making a measurement relative to the original voltage. Display will 0. Rotate C counterclockwise, and it should go negative because you're below the reference, right? Does that make sense? Are we okay? And then when you turn it positive, it's going to do what? It's going to go, when you turn it past the reference position, it should go positive. So what we're doing now, we're making measurements relative to some point that we needed. Are we okay? The hold function, what do you think the hold function is going to do? It's going to hold whatever you have when you press that button. You can disconnect your meter and you can carry it around with you. You take it up to your boss. See, I told you that's what it was, right? Press and hold the button. So press the hold button. We'll pause and freeze the screen display to hold the value for easy reference. And of course, if we press it again, it should go back to live. We okay? So that's a unique feature. Or a neat feature. I could think of some times that I would like to have that feature. Are we okay? Hold button works. We can use it with all the following. So the hold button works with everything on the dial, right? Next, we'll form the hold on a DC test as an example, but remember it can be used on any value. I thought we just did that. Connect the meter, connect the common meter, connect the DC. Didn't we just use the hold? Huh? Oh, I think here we're going to use them with all of them, though. What we're going to do instead of going to terminal 4, we're going to go to terminal 3. I think we're going to try it on frequency. I think we're going to try it on several different measurements. Set all your potentiometers counterclockwise. Turn the simulator on. Hold. The signal will be erratic. Press the hold button, and what should it do? Should freeze, right? Now the problem is when you freeze it, where's it going to freeze at? Does it freeze at the same thing all the time? Yeah. So what happens is wherever you happen to press that button, that's where it's going to freeze it. Note how the display is paused or frozen for easy reference. If you press it and release it, it's probably going to freeze at a different amount. And if you press and hold again, you'll get the live feature. Now, if we was doing this with an analog meter, we'd see it doing this. Digital meters, though, remember, it takes time to update through the D-to-A converter, and it gets very confusing. That's what's nice about this analog bar right here. Fluke was the first one that added that, by the way. What two values does the record feature capture? Yeah, maximum and minimum, right? What purpose does the relative feature perform? Yeah, from a reference point. So we can make measurements from it. We can tell if it's below that reference or above that reference, right? And what happens to the value being displayed when the hold button is pressed? Yeah, it holds it. This 4 rotary dial functions that can be utilized with record, hold, relative, and hold button. You choose the first 3, you got them, right? Because if y'all remember, the first 3 was on all of them, wasn't it? We okay? That's what that is. That's the end. So anything y'all want to go back and look at? Yes, no? Huh? That's a long lecture. Yeah. No, for this class, you need to retake it. You don't have to detail. I'm the campus administrator for NC3, so I can get any certificate I want. Huh? Well, to get credit for this class, you need to just go back and retake it again. It'll be good for you anyway. It's free.
Show up when you see it. You need to email it to you. Show up on the thing.
Yes.
Yes,
Yes. You are to pass it the second time. If you can't pass it the first time, the second time after you've been to it twice, then that's not good. Are we okay? So y'all ready? Y'all want to do this? All right.